So first thing to say about the Dirac delta function, very often used in physics, is that strictly it's not really a function because it doesn't have a value at x equals 0. If it were to have a value, the value there would be infinite, and so we don't really call it a proper function. But it's used to indicate a point source, for example. So in practice, its definition it really involves an integral. So really you can think of it as a spike, a sort of infinitely thin spike located at x equals 0. It has infinite height but 0 width, which means the area is undefined, so you actually need to define it in terms of an integral. So in fact the area is 1. If you integrate the delta function, you get the answer 1. More precisely, the way it's used is in this definition here, that if you have a delta function located at x equals x0, then if you integrate that multiplied by any function f, then if x0, where the delta function is, lies strictly between a and b, then basically you get the answer of the value of f at that point in the delta function. So for example, the simplest case is if f equals 1, then you're just integrating the delta function, and then you just get the answer 1. If the delta function is located at one of the limits of the integral, then you actually just get half, or half the value of the function. And finally, if the delta function, if this a and b, if x0 is outside the interval a to b, then you get the answer 0, of course. So the delta function is basically 0 everywhere, except at 0 if you've got delta x, or x0 if you've got delta x minus x0. You can actually define the delta function as the limit of various other functions. This is the rectangle function we'll deal with a bit later. Here you can see a Gaussian as the width of the Gaussian decreases, then you've got a normalization constant to ensure that the integral stays as 1. This is some other something which looks vaguely like a Gaussian, goes to 0 more slowly, and the sinc function is sine x divided by x. So all of these, as a goes to 0, behave like the delta function. So a related function is the step function, which is, as the name suggests, simply a step. For x less than 0, it's 0. For x greater than 0, it's 1. And normally when x equals 0, it's defined as equaling a half, though occasionally people either give it the value 0 or 1 at x equals 0. But anyway, that's not terribly important. The integral ends up being the same. The sign function, SIGN function or signum function, is also quite useful. It's very obvious definition. It's -1 if x is less than 0, +1 if it's greater than 0, and 0 at 0. And you can use this function to define the step function. Heaviside is some engineer, mathematician who came up with a function, rather simple function. So that's why it's given the symbol h. Sometimes also given the symbol theta. Okay, so properties of these things. Well, okay, as I said, if you're not at the delta function, then the value is 0. This is a useful property to know, that delta of something times x is actually 1 over the modulus of h times delta x. That you can show by changing variables. it's not obvious that it should be modulus x. You have to be careful and consider both cases when h is positive and negative if you change variables and do the maths. So as a consequence of this, it turns out it makes no difference whether you have delta of x minus x0 or delta of x0 minus x. They're the same thing. It's basically you've got h equals +1 or -1, and you end up with the same thing. So these two functions, the delta function and the step function, are related. Basically, if you differentiate the step function, you get the delta function. So that's fairly obvious. Well, the 0 bit's obvious because it's flat until you get to x equals 0, and then you've got a sudden jump. Well, really, you start off with this. If you integrate delta from -infinity to x, you get 0 unless x equals 0, in which case then you get a half, and if x is greater than 0, then you're going to get 1 by the definition of the delta function. And then, yes, if you differentiate this, then you end up with this. So this is a particularly useful property of the delta function that we'll use when we consider Fourier transforms in particular. I'm not going to justify it. And finally, we can have multi-dimensional delta functions. If we define R in n-dimensional space as x1, x2, so xn, these are the variables in n-dimensional space. And it could be x, y, z, for example. And R0 is just some point in that n-dimensional space. Then we write delta of vector R minus vector R0, which you can also write in this way. You just write as a series of x1 minus x1, 0, the coordinates, is actually just the product of delta functions in each of the dimensions. So for a simple example would be if R is in ordinary three-dimensional space, you've got x, y, z, then you'd have the delta R minus R0 is simply delta x minus x0 times delta y minus y0 times delta z minus z0. So Mathematica knows about these functions. Dirac delta behaves itself. The Heaviside step function, it's called unit step, and this is what I warned you about. In Mathematica, the unit set of 0 is defined to be 1 and not 1/2 for some reason. Sure, they got their reasons. So just to mention some related functions, top hat function is very useful, particularly when you're talking about diffraction. Or single slit experiments, that sort of thing. And when you're doing Fourier transforms, which are related things. So top hat function is basically what you got here. It's a bit like the step function, except it's a step up and then a step down again. So you can in fact define it in terms of the step function. The thing to warn you about is this pi symbol is sort of my own invention. There's no standard symbol for the top hat function. I've just used the symbol pi because it actually looks like the function itself. This is capital Pi. But yeah, some people use rect for the rectangle function, but there's no standard symbol, so no standard definition or symbol, so you have to really define it if you're going to use it. And similarly, the ramp function, sometimes useful, again is simply related to the step function. R is just x times h, so when it's less than 0 it's 0, when it's greater than x is greater than 0 it just goes up steadily like that, sometimes useful.